Today we are going to study, meaning in this video we are going to study something called the determinant of a square matrix. We will have two videos on this idea. So, in this video we will look at the determinant of small matrices. So, matrices of size 1 by 1, 2 by 2 and 3 by 3, and we will familiarize ourselves with how to compute them and some of the properties, and in the next video we will see the more general version for any square matrix. Okay. So, every square matrix A, we associate a number called the determinant of the square matrix. So, I will put in a caveat right at the start for this video and for the next. Whenever I talk about a matrix, I mean a square matrix if I do not say it explicitly. Okay. So, how do we write this number called the determinant? We usually use the notation det, so det of A, or the notation mod of A. So, which is one of these two. Okay. So, why do we want to study this? So, this is a very important question that one should ask whenever we study any concept. So, determinants are going to be used in solving a system of linear equation, in finding the inverse of a matrix, and later on when we do vector calculus, and then there are many other uses. It is a very powerful concept, and unfortunately we will not be doing all those over here, but it is a very useful concept beyond these three uses. Okay. So, let us begin with the 1 by 1 matrix. So, when you have 1 by 1 matrix, so A is it's a number with two brackets on the side. So, then the determinant is just that number, it is just A. Yeah. So, if A is bracket A, then determinant of A is the number A. Okay. So, nothing very great happening so far. So, let us look at the determinant of a 2 by 2 matrix. Okay. So, here is your 2 by 2 matrix. I have written the entries A B in the first row and C D in the second row. And how do we compute the determinant? So, we compute the determinant by looking at the diagonal. So, on the diagonal we have A and D. So, we multiply those, and then we look at the non-diagonal entries. So, we have B and C. So, we multiply those and then we subtract out BC from AD. So, determinant of A is AD minus BC. Okay. The arrows here are very crucial. So, keep those in mind. So, let us do an example. This is a just for a start. So, here is your matrix A, which is 2, 3, 6, 10. Yeah, it is a 2 by 2 matrix with those entries. So, what is determinant of A? Determinant of A is 2 times 10 minus 3 times 6. So, 20 minus 18, which is 2. Here is another example. So, 5, 2/3, 6, 3/7. So, if you multiply the diagonal entries, you get 15 by 7. If you multiply those the other two entries, you get 2/3 times 6, which is 2 times 2, which is 4. So, then we get determinant of A is 15 by 7 minus 4, which is minus 13 by 7. So, 15 minus 28 by 7, which is minus 13 by 7. Okay. So, we know how to calculate the determinant of a 2 by 2 matrix. Let us move on to a 3 by 3 matrix. So, suppose we have a 3 by 3 matrix, let us call it A, and then now we will write the entries in the way we learnt in the matrix video. So, A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. So, what is the determinant of A? So, we are going to obtain this in a very particular manner. So, we will say we will obtain the determinant by expanding with respect to the first row. Okay. So, what do we do in the first row? We write these three new expressions. So, you can see A11 highlighted here, and the entries in the first row and the first column have been deleted. Okay. So, it is not as bold as the others. Similarly, for the next entry in the first row A12, we look at the entries other than the ones in that row and column. So, we do not look at the other two entries in the first row and we do not look at the other two entries in the first column, sorry, in the second column. And similarly, we look at A13 and we neglect the entries in the first row and the third column. Okay. So, keep this picture in mind as we go ahead. Okay. So, what do we do with these entries? Okay. So, determinant of A is this rather strange looking expression. It is A11 times determinant of the 2 by 2 matrix that was left out in that first expression minus A12 times determinant of the 2 by 2 matrix that was left out in the second expression plus A13 times determinant of the 2 by 2 matrix which was left in the third expression. Okay. So, let us just work this out, because now we know how to compute the determinant of 2 by 2 matrices. So, this is A11 times A22 A33 minus A23 A32 minus A12 times A21 A33 minus A23 A31 plus A13 times A21 A32 minus A22 A31, and then we can expand the brackets and we get some rather nasty expression with 6 terms. Okay. So, this is the determinant of A. Let us quickly recall from the previous page what we had those 3 expressions were, and maybe we can rewrite these terms. So, this is what the expression for the first expression looked like. Similarly, the second expression looked like this, A12 and then A21, A23, A31, A33, and the third expression looked like A13, A21, A22, A31, A32. Okay. So, you can see what has happened. We have dropped the entries over here and over here. Similarly, here we have dropped the entries over here and in the rest of this row, and we have dropped the entries over here. Okay. Fine. So, what is the point? So, the point is that the first expression over here, this A11 is what is coming here, and then this matrix is what is coming here, and you compute this determinant. Similarly, for the second expression, you take this A12, that is what is coming here, and this matrix. So, we move it so that it is a 2 by 2 matrix and we compute its determinant, and that is what is coming here. And then similarly, A13 is coming here and this 2 by 2 matrix is coming here, and you compute its determinant. Okay. So, remember very important that over here the first entry came with a plus sign, the second entry came with a minus sign, and then the third entry again came with a plus sign. So, it alternates. Okay. These signs alternate. This is a very important property that they alternate, and this is what is maybe at the heart of this definition. Okay. So, I hope you understood how to compute the determinant or how it is defined for a 3 by 3 matrix. So, let us do an example. So, here is an example. So, A is this matrix here, 2 4 1 in the first row, 3 8 7 in the second row and 5 6 9 in the third row. Let us see how to compute it. So, the 2 goes, you first look at the first the 1 1 entry, which is 2. So, that is over here. Then look at whatever is remaining when you drop everything else in that corresponding row and column. So, that is what came here, and compute its determinant, multiply them. Then you look at this 4 came here, very importantly with a negative sign. You look at 3 5 and 7 9, and that matrix is what comes here. You take its determinant, multiply them, and then plus the third term, which is you take this 1 here and then take the matrix left out, which is 3586 after you drop everything else in the corresponding row and column to the 1, right. And now we know how to compute determinants of 2 by 2 matrices. So, from there we will be able to compute this determinant. So, let us complete the calculation. So, this is 2 times determinant of this 2 by 2 matrix 8, 7, 6, 9. So, 9 times 8 is 72, that is what we get in the first term here, minus 7 times 6 is 42, that is what we get in the second term here. Similarly, here we have minus 4 times determinant of 3, 7, 5, 9. So, that determinant works out to be 3 times 9 minus 7 times 5, which is 27 minus 35, and then plus 1 times determinant of 3, 8, 5, 6, which works out to 3 times 6 minus 8 times 5. So, that is 18 minus 40. So, that is how you get this expression, and the rest of it is a standard computation, which if you complete you will get you should be getting 70. Okay, so, I hope this example explained to you how to compute the determinant in case you got lost in the previous expressions. So, it is a very simple calculation. Maybe the important question is why we are indeed interested in this, and very soon in a couple of videos we will answer that question. Okay, so, let us look at some special determinants. So, remember that we had some special matrix called the identity matrix. So, that was a matrix which had 1 in the diagonal entries and zeros everywhere else. Okay. So, the identity matrix of size the 2 by 2 identity matrix, that is 1 0 0 1, and what is its determinant? It is 1 times 1 minus 0 times 0, which is 1. Okay. Now, let us do the 3 by 3 determinant. So, maybe this one I will work out the details over here. So, for determinant of I3, let us remember what we want, how we got this expression. So, determinant of I3 was, so you look at the 1 1 term, that is 1 times determinant of whatever you get after dropping everything else in that row and column. So, you drop these 0 0 and 0 0 and you write down this matrix. So, this is 1 0 0 1, aha. So, this is the 2 by 2 identity matrix, okay. And then you subtract out, you take the 1 2 term and determinant of whatever you obtain after dropping that the first row and the second column. So, which is 0 0 0 1. You can see here we do not really need to do this computation because I have a 0 times something, but I am just writing down the expression, and then plus you look at the 1 3 term, which is again 0 times determinant of whatever you get after dropping the first row and the third column, which is 0 1 0 0. Okay, this is the expression for the determinants, and as we noted, we do not really need to compute anything here because this is just 1 times determinant of I2. The other two terms do not contribute anything because they are zeros, and determinant of I2 we have computed upstairs, it is 1. So, this is 1 times 1 is 1. Okay. So, I hope this showed you that the determinant calculation is really quite straightforward, and the determinant is computed in a sort of inductive way, meaning if you want to compute the determinant of a 3 by 3 matrix, the computation reduces to determinants of a 2 by 2 matrix. Okay. Okay. So, this is an important idea which you should keep in mind as we go ahead. Fine. So, let us look at some properties of the determinant. So, now just to recall, we know what is the determinant of a 1 by 1 matrix, of a 2 by 2 matrix and of a 3 by 3 matrix. Okay, so, let us go ahead. So, suppose we have a product of matrices, we know how to take the product of matrices. So, let us say we have two 2 by 2 matrices A and B. So, A is A, B, C, D and B is E, F, G, H. Okay. So, let us compute A times B. A times B is AE plus BG, AF plus BH, CE plus DG and CF plus DH. So, this is obtained by multiplication of matrices as we have seen in the previous video. Okay, let us compute what is the determinant of A times B. Okay. So, determinant of A times B by definition is you take the diagonal entries. So, that is AE plus BG times CF plus DH minus you take the product of the non-diagonal entries. So, AF plus BH times CE plus DG. Yeah, so just to recall for you, this was how it worked, right. Okay. So, that is what we have done. So, now let us expand the brackets. So, if you expand the brackets, you get AE times CF plus BG times CF plus AE times DH plus BG times DH minus AF times CE minus BH times CE minus AF times DG minus BH times DG. Yeah, as you can see, this is something you should probably try to do on the side on your own. These are rather long expressions. Okay. So, let us see what we get from there. So, what we get here is BG times CF plus yeah, so there is some cancellation, right. So, BG times CF plus AE times DH. So, what got cancelled? The AECF got cancelled with the AFCE, and then the BGDH got cancelled with the BHDG. Okay. So, we have 4 terms remaining in this expression. So, we get BG times CF plus AE times DH minus BH times CE minus AF times DG. Okay. So, let us now put these terms in a particular way. So, we will write this as BC times FG plus AD times EH minus BC times EH minus AD times FG. So, what have we done? We have taken the entries coming from A first and the entries coming from B next. Okay. So, you can see some terms are common here. So, let us take the common terms out. So, if you do that, we are going to get AD minus BC times EH minus FG. So, the first term here is exactly determinant of A, right, AD minus BC, and the second expression here is exactly determinant of B, EH minus FG. Okay. So, what does this show? This shows that if you take two 2 by 2 matrices and take the product, then the determinant of the product is the product of the determinants. Okay. Determinant of AB is determinant of A times determinant of B. Okay, and you can check that this works for 3 by 3 matrices as well. So, that is going to be a slightly longer argument with more expressions involved, but it will work out exactly the same way. Okay. So, you will have to just play with more terms. So, I won't explicitly show this, but believe me on this, or rather I would say work it out for yourself. Okay. So, let us go on and ask ourselves, what is the determinant of the inverse of a matrix? Can I compute it from the determinant of a matrix? We define the inverse using this identity. So, the inverse satisfies A times A inverse is I, the identity matrix, and we can work out that A inverse times A is also I. Okay. So, now we want to talk about the determinant of the inverse. So, let us take determinant on both sides. So, if we do that, we get determinant of A times A inverse is determinant of I, but we just saw that the determinant of a product is the product of the determinants. So, determinant of A times A inverse is the same as determinant of A times determinant of A inverse. Okay. And on the other hand, determinant of the identity matrix we have computed to be 1. So, what does this mean? This means that determinant of A inverse is 1 by determinant of A. Yeah, or I can write this in more fancy way as determinant of A to the power minus 1. Yeah. So, determinant of A inverse is the reciprocal of the determinant of A. So, it is 1 by determinant of A. Okay. So, so we know explicitly how to compute the determinant of the inverse from the determinant of A. Let us look at some properties of the determinant. So, let us see what happens if we switch two rows. Okay. What does that mean? So, here is A, which is A, B, C, D. Let us define A tilde by switching the first and the second row. Okay. So, what happened in A tilde? You swapped the first and the second row. Yeah. So, C D came first and then A B was next. Okay. So, that is A tilde. So, we have switched two rows. Let us compute determinant of A tilde. So, determinant of A tilde is C times B minus D times A, which we can rewrite as minus of A D minus B C, which is exactly determinant of A. So, this is minus determinant of A. So, what happened when we switched two rows? We saw that the determinant of the new matrix was the same as the determinant of A, except that it picked up an extra minus sign. So, it is minus of determinant of A. What happens when we switch two columns? So, let us do that same computation with switching two columns. So, when we switch two columns, so let us call it maybe A tilde tilde. So, let us take the same matrix A and switch these two columns. So, we get B D A C, and what is its determinant? So, its determinant is B C minus A D. Yes, and I think you can identify this expression. This expression is exactly minus of A D minus B C, which is minus of determinant of A. Okay. So, the statement for rows also holds for columns, namely if we switch two columns, the determinant of the new matrix is the same as the determinant of A with a minus sign. Okay. And the same thing can be checked for a 3 by 3 matrix. So, this is also true for 3 by 3 matrices. Okay. So, I will leave that to you to check. Yeah, it is a pretty easy check, not hard at all. Okay. So, let us look at another property. If you add the multiple of a row to another row. Okay. So, what do we mean by that first of all? So, here is A, you have A is A B C D, and A tilde is A plus T times C, B plus T times D, and then C D. Okay. How did we get A tilde? Well, the first row of A is A B. So, to this row we added T times the row C D. Okay. And what we got was A plus T C, B plus T D. So, here the T times the second row was added to the first row. So, remember here that when we say multiples here, they could be fractional multiples as well. It need not be integer multiples. Okay. Okay. So, let us see what happens to the determinant. So, let us compute determinant of A tilde. So, determinant of A tilde is A plus T times C times D minus B plus T times D times C, and let us expand the bracket. If you expand the bracket, you get A D plus T times C D minus B C minus T times D C, and you can see that the T times C D and the T times D C cancels out, and we are left with A D minus B C, which is exactly determinant of A. Okay. So, what happened? If you added a multiple of one row to another row, took that new matrix and computed its determinant, you got back the determinant of A. So, the determinant does not change under this operation. Okay. Let us see what happens for columns. So, suppose I add T times the second column to the first column. Okay. So, A plus T times B, A plus sorry. C plus T times D, and then this is still BD. Okay. So, now what have we done? We have added T times the second column to the first column. Okay, this is our new matrix A double tilde. Let us compute determinant of A double tilde. So, that is the product of the diagonal entry. So, A plus TB times D minus the product of the non diagonal entries, which is B times C plus T times D. So, that gives us AD plus T times BD minus BC plus B times TD, and you can see what is happening. T times BD and B times TD are going to cancel. I have incorrectly put a sign, they should be minus. Sorry. So, now what we get here is AD minus BC, which is exactly determinant of A. Okay. So, what happened? If you added a multiple of one column to another column, then the new matrix obtained has the same determinant as the original matrix. Okay. So, under this operation, the determinant remains unchanged. Okay. And you can check this for 3 by 3 matrices. Okay. So, the same results will work. Okay. And finally, let us look at what happens when we multiply a row by a constant t. Okay. So, suppose A is A, B, C, D, and suppose we multiply so I think I made a mistake in the example. So, here we are multiplying a column and not a row. So, suppose we multiply this column by t. So, we get A, T, B, C, T, D. Okay. So, let us find out what the determinant of A tilde is. So, determinant of A tilde is A times T D minus T B times C, which is, if you take T common, so T times A D minus B C. So, this is exactly T times determinant of A. Okay. And now, let us do what we originally intended to do as in the title. So, suppose A double tilde is T times A, T times B, C, D. Okay. So, in that case, determinant of A double tilde is T times A times D minus T times B times C. You can take the T common. So, you get T times A D minus B C, which is T times determinant of A. Okay. So, what have we shown? We have shown that if you multiply a particular row, meaning every entry of that row, by some constant t, or you take some column and multiply every entry of that column by some constant t, then you compute the determinant of this new matrix, then the determinant of the new matrix is t times determinant of the original matrix. Okay. And again you can check that the same thing happens. So, same results hold for 3 by 3 matrices. Fine. So, we have seen some properties of the determinant. So, let us quickly recall what we did today. We have defined something called the determinant for square matrices of size 1 by 1, 2 by 2 and 3 by 3. We saw that for the 3 by 3 case, they were defined by using what was the definition for the 2 by 2 case. Yeah. So, some kind of inductive definition, that is what we will call it. And then we saw some properties. A very important property was that if you take the product of two matrices, then the determinant of that product is the product of the determinant. So, determinant of A B is determinant of A times determinant of B. Then we saw the inverse of a matrix has determinant inverse of the reciprocal of the determinant of A. And then we saw some other properties which the determinant satisfied, namely, if you multiply a row by a constant or a column by a constant, that constant comes out of the determinant. If you add a multiple of one row to another or one column to another, then the determinant is unaffected, and if you swap rows, then the determinant picks up a minus sign. Okay. So, with that I think we will end this video. Thank you.